Good morning, class. So today I want to describe to you section 5 of chapter 6, and that's what happens to air as it expands and compresses. And so what we're going to do is we're going to take a look at a parcel of air. So let's go ahead and draw that. So here we are at the surface. And we have a parcel of air. So a parcel of air is basically a bubble of air or a balloon of air, kind of hypothetical concept. And we're going to force this parcel of air to rise. Okay, and so we'll talk about why air rises a little bit later in this chapter. But as we force this parcel of air to rise, a whole series of dominoes are going to fall. So first of all, we get that air to rise. Air rises or ascends up in the atmosphere. And as the air rises, its pressure is going to decrease. Okay, so remember the definition of pressure is the force exerted by the weight of the air molecules above us. So as we go higher up into the atmosphere, there's fewer air molecules above us. And so as a result, the pressure is going to decrease. When the pressure decreases, the third thing that happens is when you decrease the pressure, the air is going to expand. And we can draw that now as we got this air parcel at the surface, we forced it to rise. As the air rises, the pressure decreases, the air expands, and as the air expands, then that air parcel, the bubble, is going to get bigger as it goes up into the atmosphere. As the air expands, the density of the air is going to decrease. Because here, for example, maybe we have, let's see, 5, 6, 7, 8, 9, 10. Let's say that this air parcel has 10 air molecules in it. It will still have 10 air molecules in here. 3, 4, 5, 6, 7, 8, 9, 10. Okay. So density is, in this case, the number or the mass of air molecules per volume. So our mass or number of air molecules didn't change, but the volume of the air parcel got bigger. And so density is the mass or number of air molecules per volume. If the volume increased, but the mass or number of air molecules stayed the same, then our density decreased. And when our density decreases, then our air temperature is going to decrease. Okay, so you see all of these things going on as air rises. As the air rises, the pressure decreases, the air expands, the density decreases, and the air temperature decreases. Now remember, what we said earlier in this chapter is that if you know the air temperature, you know the saturation mixing ratio. If you know the saturation mixing ratio, you know the air temperature. It works back and forth off of that saturation mixing ratio table. So if the air temperature is decreasing, then we know that the saturation mixing ratio of the air is going to decrease. Okay, now think back to our equation for relative humidity is the mixing ratio divided by the saturation mixing ratio. And so if the saturation mixing ratio of rising air is decreasing, okay, that means that our denominator is decreasing. If our denominator is decreasing, then the overall number, the relative humidity, is increasing. So typically, as air rises, pressure decreases, the air expands, the density decreases, and the air temperature decreases. Therefore, saturation mixing ratio decreases. If saturation mixing ratio decreases, then relative humidity will typically increase as air rises. Okay? And if we take this to another higher level in the atmosphere, all of these steps are going to apply. The air is going to rise, continues to rise, the pressure is going to continue to decrease, the air is going to expand, so our air parcel is going to be even bigger as it goes up into the atmosphere. The density is going to decrease because we still have 10 air molecules in this volume. I didn't count hopefully there's 10 there. So our air temperature is going to continue to decrease, the saturation mixing ratio is going to continue to decrease, and therefore the relative humidity will increase. Okay? So that's what happens to air as it expands, okay, as it rises and expands, but whatever goes up must come down. So now let's take this, this air parcel and let's bring it back down to the surface. Okay, so here we have an air part. You can use the same air parcel if you want, and we're going to cause this air parcel to descend. And maybe it's descending down the lee side of a mountain. It went up the windward side of the mountain. It's coming down the lee side of the mountain. So let's see what happens here. So the air is going to descend. And as the air descends, then the air pressure is going to increase. Okay, so again, pressure is the force exerted by the weight of all of the air molecules above a given point. So if the air parcel is descending, now you've got more air molecules above it as it continues to descend, and so the air pressure is going to increase. As the air pressure increases, the air is going to compress. It's going to get, the volume of that air is going to get smaller. So as we draw it here, that parcel of air is going to get smaller, okay, as it compresses. And as it compresses, now the density is going to increase. Okay. You have, again, the same number of air molecules in that parcel of air, the same mass of air molecules in that parcel of air, but the parcel's getting smaller, the volume's getting less, and therefore the density is going to increase. If the density of the air is increasing, that means that the air temperature is going to increase. Okay, and as the air temperature increases, remember, if you know the air temperature, you know the saturation mixing ratio. So if the air temperature is increasing, the saturation mixing ratio is going to be increasing. Okay. And so now we can draw our surface down here. We can continue to bring that down to the surface. So our air parcel is going to be, again, smaller. Okay. Now, getting back to our saturation mixing ratio is increasing because the air temperature is increasing. So again, remember our equation for relative humidity, mixing ratio divided by the saturation mixing ratio. If the saturation mixing ratio is increasing, okay, and that's the denominator of our equation, if the denominator is increasing, then our overall number, the relative humidity, is decreasing. And so as a result, the relative humidity of the air is going to decrease. Okay. And so that's what happens to air as it expands and compresses. And the compression, it's the expansion part we're going to be talking about most for the rest of chapter 6. But just as an example for the compression, if you've ever traveled out into the mountainous states, you'll notice that the windward side of mountains tends to be kind of green and lush. That's because as the air rises, it cools and the relative humidity increases, and you get clouds and precipitation much more frequently on the windward side of mountains. And then on the leeward side of mountains, where the air descends and it compresses and the temperature increases, so the relative humidity decreases, you'll notice that cloud cover typically is less common. Precipitation is much less on the leeward side of mountains. And so the leeward side of mountains tends to be kind of dry and drab because they don't have as much precipitation. So, the mountainous states are good examples then for why you have green, lush vegetation on the windward side of mountains and kind of dry and barren conditions on the leeward side. So windward side of mountains, leeward side of mountains, green lush, windward side, kind of dry and drab, brown conditions on the leeward side of mountains. Okay? So if you have questions, make sure you let me know. All right, talk to you later. Bye-bye.